Welcome back. As you know, your exam starts today. It's over in the testing center. You can take it today if you want to. Yay. Or tomorrow. It closes Monday. Testing center hours are a little bit different over the weekends and on Monday, so pay attention to that. Make sure you give yourself plenty of time. The amount of time it usually takes on average, of course there's a distribution of values, is about 2-ish hours. The exam's 20 questions long. It's worth 183 points, meaning some questions are worth 10, 3 of them are worth 10, the remaining are worth 9 each. So good luck. I don't think there'll be any surprises, but do your best. Okay, so what we're going to do today is show you some interesting biological examples of nucleophilic acyl substitution. This is going to set the framework for you so that you can know what's going on in biology, even if they don't push arrows for you to show you the mechanisms. The first idea is we want to talk about an antibiotic that at least some of you in your futures hope that you might be able to prescribe to people as physicians. And that is a class of antibiotics called beta-lactams. And likely, if you've ever been to the doctor for an ear infection or some kind of sinus infection, they've probably prescribed, or at least attempted to prescribe, a beta-lactam antibiotic. So the term beta-lactams actually, it comes from the chemical structure of the molecule. And the key part is a 4-membered ring in which one of the atoms is a nitrogen, and it's involved in an amide bond. Now, at the start of this, I want to address the question that's going to be asked at least a couple of times during this lecture is, so do I need to memorize the stuff that you drew up there? The answer is we're not real big on memorizing stuff today. There will be a time for memorizing biological structures. We'll do that later on in the class, but today is not that day. Your goal here is to apply chemical principles and to see the examples of nucleophilic acyl substitution. Nucleophile attacks carbonyl carbon to give a tetrahedral intermediate, which collapses and the leaving group leaves. So there's going to be a lot of drawing of unfamiliar molecules. You're going to be overwhelmed. It's a fire hose kind of day. But you need to relax your eyes just a little bit and focus on the general chemical principles. So where does the term beta come from? This is the carbonyl carbon, this is the alpha carbon, and this is the beta carbon. A lactam is a cyclic amide. A beta-lactam is a cyclic amide where the nitrogen is attached to the beta carbon. So that is why that key structure is a beta-lactam. And as you might expect, that 4-membered ring is strained, and that actually plays a role in its function as an antibiotic. The 4-membered rings actually fuse to a 5-membered ring. Again, we're not looking at memorizing structures, but it's helpful to see what these things look like. There is sort of a side chain here that's a carboxylate. And then what I'm actually drawing for you is the structure of amoxicillin. There's another nitrogen here, and then a carbonyl carbon, an NH3 group, a benzene ring, and an OH group. So we're not going to talk about all of the rest of the structure. We're basically going to focus in on this 4-membered ring. So yeah, the chemistry is going to be dominated by the fact that this is a strained 4-membered ring. And that's important for you to realize because beta-lactams are going to be reactive at the carbonyl carbon. And you should be suspicious of that because you've learned that amides are very stable. A negatively charged nitrogen is not a good leaving group. Amides are pretty low down in terms of reactivity. And so you should be suspicious that I'm telling you that this type of molecule could undergo nucleophilic acyl substitution with some nucleophile attacking the carbonyl carbon. Nevertheless, what's going to pay for that is the relief of the ring strain in the 4-membered ring. So let's show you what these antibiotics actually do and the process that they're designed to inhibit. Beta-lactam antibiotics inhibit what's called bacterial cell wall synthesis. So, take a deep breath because we're about to draw something that's horrific. It involves chairs. So, are you ready? Let's do this. All right, so you've got sort of a glucose type carbohydrate linked to another glucose type carbohydrate. Oh, brother, I'm going to get that wrong, aren't I? Probably not. Okay, and these are actually polymers. So we'll put squiggly lines to indicate we're zooming in on what's called the peptidoglycan part of bacterial cell walls. Glycan refers to a carbohydrate, so that's the core 6-membered rings that are each linked together. There are going to be branching hydroxymethyl groups on that carbon. There's going to be an equatorial OH group here. And then there's going to be, instead of an OH group on this carbon, a nitrogen that's attached to an acetyl group. I'm just going to abbreviate that as AC for now. Okay, so that's 2 N-acetylglucosamine residues. You don't need to know that name today, but there's 2 sort of carbohydrate chains, and then one of them has an OH that's bonded to a bunch of other things. So take a breath because it's going to continue to get worse. You thought that was bad. It's going to get worse before it gets better. So there's a stereocenter here. This is an amino acid that's actually attached to one of the OH groups of the carbohydrate. That amino acid happens to be called threonine. Then here's another one with a methyl group there, and a carbonyl carbon and a nitrogen. I wouldn't be doing this if this weren't what nature actually does. There's another amino acid with a carboxylic acid side chain there. When I did this last semester, I just pasted the pictures up like slides and we talked through it. I'm beta testing, giving you a chance to draw it today. We'll see whether you like that or not. If you're like, just give me the notes, then maybe we'll do something different next time. 1, 2, 3, 4, 5, 6. All right, we'll put an R group on that nitrogen. That nitrogen's attached to something else, which is important, but not important for our story today. NH, and we're almost done drawing this part of the molecule. Okay, there you go. So this is a subunit of bacterial cell wall peptidoglycan. And one of the things you need to know about bacterial cell walls in terms of what they're trying to do is bacteria want, here's a carbonyl carbon, there's a carbonyl oxygen. For a moment, I'm going to erase this R group and have it just be, have an R group, and then on the end we're going to put a nucleophile, just a generic nucleophile. Bacteria want one subunit of cell wall to be cross-linked to another subunit of cell wall. Basically, and you don't have to copy this down, right? And it's not important totally for our discussion today. But what bacteria want to do is they want to have this nucleophile attack this carbonyl carbon and do a substitution reaction, a nucleophilic acyl substitution, that if we kicked off all of this as a leaving group, would leave a cross-link between this nucleophile and the blue carbon. Do you see how that a new bond between the purple nucleophile and the blue carbon would link 2 subunits together? That provides some rigidification to the bacterial cell wall and helps them survive challenging and difficult conditions. It's like a cross strut on an engineering bridge or something like that. I don't know, civil engineers out there can forgive me for not knowing what I'm talking about. So what the beta-lactam is going to do, well, there's an enzyme that does this, that catalyzes this cross-linking process. The enzyme will do a couple of things. The enzyme's first, nope, there we go. The enzyme first has to activate the carbonyl oxygen so that it can be attacked. And that probably looks like some kind of hydrogen bond. I won't draw that here, but you could imagine, well, maybe I will and then I'll erase it. You could imagine some kind of functional group in the enzyme active site that would hydrogen bond with that carbonyl oxygen and make it, if not a full oxonium ion, not fully protonating the oxygen, at least close to it. The idea is you want to stabilize the buildup of negative charge as the nucleophile attacks the carbonyl carbon, okay? And then the other thing the enzyme is going to provide, and here is the Pac-Man enzyme. There it is. Mouth is open really wide. This is called glycopeptide because it acts on bacterial peptidoglycan. Glycopeptide transpeptidase, which basically means it's going to interchange amide bonds. And this glycopeptide has a negatively charged oxygen in the active site. How did it get that? It probably started out as just an alcohol, and then there's probably a base in the enzyme active site that deprotonates the alcohol so that the enzyme can then have this negatively charged oxygen that does the attacking. Okay? So the enzyme is going to first use its own oxygen as the nucleophile. I'm sorry, I can't resist. We just got to color the enzyme so it looks like Pac-Man a little bit. Okay, the enzyme is going to attack the carbonyl carbon, create a tetrahedral intermediate, and then this leaving group is going to get kicked off, and the enzyme will be bound to the molecule, and then some other steps are going to happen. We don't need to worry about those today. In the end, though, the enzyme is going to catalyze a cross-link between bacterial cell wall subunits. Now, enter the beta-lactam antibiotic. The role of the beta-lactam antibiotic is to fit in the enzyme active site in the place of this segment of bacterial peptidoglycan. Now, just looking at those structures, they don't look that similar at all, right? That's because we've drawn them on paper and you're not getting a totally clear picture of their three-dimensional structure. But it turns out that this amoxicillin beta-lactam antibiotic fits pretty well in the enzyme active site. And a large amount of current drug development today and over the past 50 years has been designing molecules that fit in enzyme active sites better than the stuff that's supposed to go there. So what happens when the enzyme encounters a beta-lactam antibiotic is it gets diverted from what it was supposed to do, and instead it attacks the carbonyl carbon of the beta-lactam, and you get a tetrahedral intermediate. Let's just, for fun now, draw what that tetrahedral intermediate would look like. Fun, right? Having fun. But we're not really introducing anything new here. Let's see. So I'm going to draw the beta-lactam antibiotic in about the same way. Here's the negatively charged oxygen in the tetrahedral intermediate. And then here is the oxygen from the enzyme, which we're going to draw like that. We'll just keep it small if that's okay. Then we'll do the rest. Of the molecule. And I'm just going to put an R here for the rest of the beta-lactam antibiotic. Okay, So now you have this tetrahedral intermediate, and you predict that nitrogen is not a particularly good leaving group, but if it left, you would relieve ring strain. So some of the relieved ring strain pays for the fact that nitrogen is not a good leaving group. The other thing that likely happens is that nitrogen is going to be close to a group that can protonate it as it's leaving, some acid, perhaps from the enzyme. So what's going to happen is electrons kick down, nitrogen leaves, that relieves ring strain, and then let's draw what happens afterwards. I'm going to draw the molecule in about the same way, only I'm not going to attempt to keep it in sort of a square shape because we've just relieved a bunch of ring strain. Here's the new carbonyl, here's the same old carbonyl carbon, the carbonyl oxygen, and then here's the substitution product where the Pacman glycopeptide transpeptidase is now attached via an ester to the enzyme. Now imagine what that does to the enzyme. What used to be the nucleophile in the enzyme is now tied up in an ester, and this is reasonably stable. And in terms of the enzyme's ability to catalyze more reactions, the enzyme has been inactivated because the purple oxygen, which used to be negatively charged, is no longer a good nucleophile. So the beta-lactam acylates. That's one other way of talking about a nucleophilic acyl substitution reaction. The beta-lactam acylates the enzyme and thereby inactivates it. Okay, questions about that? When you take amoxicillin, that's what's going on. Now, go ahead.
So it doesn't actually break the cell walls of the bacteria, it just stops it from synthesizing?
Yeah, it doesn't. In a way, the beta-lactam weakens bacterial cell walls by stopping the enzyme that reinforces them. And then because the cell walls are weaker, the bacteria are more vulnerable to your immune system and you can clear the infection better. Okay, others? All right, let's talk bacterial resistance. So as you know, this is a major and important topic in modern medicine. Bacteria have been able to evolve ways to evade beta-lactam antibiotics. And so there are some strains of bacteria that are resistant to conventional antibiotics like beta-lactams. So we won't talk about this today, but there are a class of enzymes, and actually we use them in biochemistry all the time. There's a class of enzymes called beta-lactamases. And these are enzymes that can hydrolyze beta-lactams so that they don't acylate the glycopeptide transpeptidases. So if your bacteria happens to have beta-lactamases, it's going to be able to hydrolyze the lactam. And as you can see, that four-membered ring is really important, right? You need the four-membered ring there so that relief of ring strain, which I'll just note here, relief of ring strain helps pay for that nitrogen to leave. If the four-membered ring isn't there, it's no longer a good acylating agent for the bacteria. So we won't say too much more about that, but you may hear about beta-lactamases in the future. And we use these as a tool to select for bacteria that have certain properties in biochemistry. Okay, so that was story part one. Part two of our story about nucleophilic acyl substitution reactions involve what I've told you are what we've seen before a little bit in a previous chapter and what we've talked about before, but acyl phosphates and thioesters. So thioesters are pretty simple. You have a sulfur in place of the oxygen from an ester. I'm just going to let that be we'll let what's on the sulfur be an R group. And as we've said, thioesters are reactive in nucleophilic acyl substitution reactions because the Sr minus is a decent leaving group. Not as good as Cl minus, but certainly okay. And you can tell it's a decent leaving group because its conjugate acid has a pKa of around 8. Meaning that at physiological pH, about 10% of thiols are negatively charged. I also told you that acyl phosphates, in which we have a leaving group that looks like this, or a leaving group that looks like this, where one of the OHs on the phosphate is actually an OR group. These are also decently good leaving groups. We can draw what they look like once they've left. And the conjugate acid is the phosphate monoanion, which has a pKa, as we learned a couple times ago, of 7. And you know what we've done here, it would, for just the phosphate group leaving, wouldn't really be changed that much if we replace the OH here with an R group. And I'll draw what that R group is a little bit later. But the basic concept is both of these have a carbonyl carbon and a carbonyl oxygen, and nucleophiles can attack, and then the leaving group can leave. So, I can show you how acyl phosphates are made, and maybe we'll do that a little bit later, but I just want to give you some examples of reactions involving acyl phosphates in biology. All right, so here's one that's involved in the synthesis of the amino acid glutamine. You start out with an amino acid where the side chain has an acyl phosphate. We'll just draw it like this. Again, carbonyl oxygen, carbonyl carbon, and here's the leaving group. And then nature will use ammonia. That ammonia is probably, as a nucleophile, that ammonia is probably delivered using PLP, kind of like we've, via an enzyme that has PLP carrying it around. But anyway, imagine just using this nucleophile in the first step to attack the carbonyl carbon to get a tetrahedral intermediate. I won't draw that intermediate or the proton transfer steps. Well, maybe I'll draw one of the intermediates along the way, the intermediate that immediately precedes the leaving group leaving. You'll see that by the time we get here, you have to have done a proton transfer step so that the nucleophile is now, it's no longer a leaving group. And then we'll have the negatively charged oxygen kick down and the leaving group leaving. And that makes the final product, which is the amino acid glutamine, and phosphate is the leaving group. So what's that going to look like? That's going to look exactly what we started with, only we will have substituted an NH2 group in the place of the phosphate group. And then the phosphate here is the leaving group. Again, you're going to be tempted, if I were to ask you to propose a mechanism for this reaction, you're going to be tempted to do what's exactly wrong. You're going to be tempted to have the nucleophile come in and the leaving group leave all in the same step, as though it's an SN2 reaction. And it's not, right? Because the LUMO is the pi star. The nucleophile has to attack the pi star. You have to get a tetrahedral intermediate, and then the leaving group leaves. And there is really good evidence that that's true. Just as a warning, sometimes people in various talks that they might give about biochemistry, or sometimes even in biochemistry texts, a text will summarize a nucleophilic acyl substitution by doing that, which I hate because it tells you that you think the mechanism is SN2 versus this addition to make a tetrahedral intermediate followed by elimination to get the substitution product. So in my class, you're always going to draw the mechanism this way. If you see a nucleophilic acyl substitution mechanism where they're just going like this, understand that that's shorthand. Perhaps slightly better is what some people will do because they don't want to draw the tetrahedral intermediate, but they want you to know that they know it exists, is they'll do something like this, whoop, which I hate as well. So don't do that, okay? All right, questions about that? Yeah?
So on that final molecule there, on the left, you have positively charged nitrogen, and on the right it's neutral.
Right. Why is this nitrogen positively charged and this one is neutral? Lone pairs on that nitrogen, this is an amide functional group. You need to get used to recognizing or at least seeing that amides are not amines. So it can be tempting to generalize and say, oh, those are two of the same thing. They're actually not because of resonance with the carbonyl. Lone pairs on that nitrogen are not very basic because they're stabilized with resonance, and that's true for amides. We never worry about protonating nitrogens on amides. We always worry about protonating nitrogens on amines. Okay, what else? Yeah?
Do you have magnesium to activate the carbonyl and the phosphate?
So do you have magnesium to activate the carbonyl and the phosphate? Yes, often magnesium, which is a divalent cation, is often, we might call it a cofactor or necessary in the enzyme active site. Magnesium is nice because it's got a doubly positive charge, it can interact with multiple things. So you could imagine magnesium hovering here between the two, stabilizing the tetrahedral intermediate and ultimately helping the phosphate leave. Yep, magnesium is almost always involved when phosphate's doing stuff. Yeah, others? Okay, let's do one that involves an acyl phosphate forming a thioester. This is one you're going to hate, but that's okay. I don't make up biology, I just tell you about it. So, what we'll do now is in a step involved in synthesis of triglycerides and fatty acids. So we'll just be general and put an R group over here. You start with a carboxylate, and then you use ATP, and you end up generating a weird version of an acyl phosphate. This is one of the versions of an acyl phosphate where the phosphate itself is attached to something else. And today, since we're focusing on the chemistry of the acyl phosphate, I think I'm probably not going to take the time to show you this reaction of the carboxylate reacting with ATP. It's not that difficult. I think we'll do it again later on in the class when we talk about metabolism. I think it'll fit better there. I did it last time I taught the class at this point, and I think it was just unnecessarily confusing. So I think we'll leave it off. All right, there's an acyl phosphate. I've normally said this is an R group, but behold the R group. I feel like when I say behold, I should be talking like Heinz Doofenshmirtz. Behold! Evil! Perry the Platypus. All right. Been working on that. Yeah, you're going to have that forever. I mean, so don't actually go do this, but if you were bored, in the early days of COVID, when we first switched to, this was like the spring of 2020, I sound like I'm in the spring of 1820. No, in the spring of 2020, we had switched abruptly to this, and morale was kind of low. So as I was recording lectures from home, I added in some lecture intros that usually involve me dressing up in some kind of costume, like a Darth Vader costume, or I did the prison Mike bit from The Office, which I now regret. And then I did this extended scene of Gollum talking to Smeagol. So if you want to go back to the early 2020 Winter 350, whatever it was, playlist, you may find some interesting things there. Don't hold me to it, and please don't. Well, anyway. I put it up on the internet, so I can't tell you not to do anything. There it is. But we were just bored and tired and needed some entertainment. So, okay, here is an acyl phosphate. See, you were distracted while we were drawing that whole molecule, and it wasn't as bad as you thought it was. This is, in yellow, is the whole leaving group. Okay? This is actually called it's a kind of acyl phosphate called an acyl AMP. AMP stands for adenosine monophosphate. This group here is adenine. You'll encounter that when we talk nucleic acids. This is a ribose ring. Together they are adenosine, and then this is the single phosphate. So your biochem texts may abbreviate this as OAMP, and that's fine, but this is what they're talking about. Nevertheless, for reasons we've discussed, as you can see, with that R group there, doesn't change the fact that the phosphate will be a good leaving group because its conjugate acid has a pKa of around 7. So this is a convenient AMP, this is a convenient leaving group. Now, why does nature ever use the AMP instead of just the phosphate? That seems inefficient, right? Well, remember what nature has to do. Enzymes need to grab onto the right things and not the wrong things to do reactions. So at least some of this probably involves binding to the right enzyme. As you know from what you've learned so far in your life about DNA, adenine has hydrogen bonding and hydrogen bond donating and accepting groups that could interact with things in an enzyme active site. So you can think of this as the handle that the enzyme holds on to position this molecule in the right place. There's probably more details. If you want to learn more about it, you can do that in biochemistry, or you can go look up the structures of enzymes that bind these acyl AMPs. But at least some of this has got to be binding correctly to the enzyme active site. But for us, it's a good leaving group. So this allows you to practice an important skill, which I'm hoping you're picking up, which is learning to focus in on the part of the molecule that matters and temporarily ignore the parts that aren't particularly relevant. Once you've recognized this as a leaving group, then everything else about the chemistry is going to be as easy as though you had redrawn the molecule like that, with the big leaving group on there. Okay? So nature will actually use acyl AMPs to make thioesters. So I told you it was going to get worse, and it is, because this is the acyl AMP. Nature likes thioesters to do a lot of things. Thioesters are reactive, but they also are relatively stable. I might say kinetically stable. What that means is they don't react quickly with water. They're not okay in water permanently, but they can survive being in water. So a thioester is a great way to carry around an activated carboxylic acid with a good leaving group without there being a lot of bad things that can happen to it immediately. And there are other reasons why nature would like to have thioesters as well. Some of them have to do with the enzymes that do fatty acid synthesis and fatty acid metabolism. So here is our leaving group for now the acyl phosphate is going to be, we'll call it the acyl AMP, is going to be our electrophile. So our nucleophile to make a thioester should be a thiol. And this one is, you're going to look at it and say, oh man, that's unnecessarily complicated. So here is the sulfur that's going to do the nucleophilic attack. And I'm going to draw what's here for you, but fear not, we're going to abbreviate it a little bit later. So there's 2 carbons, and then a nitrogen. And I got to save myself space. That nitrogen's involved in an amide bond. Then there's 2 more carbons and another nitrogen. And then another amide bond. Sorry. A branching OH group here, another carbon, 2 methyl groups, because why not? Another oxygen. And then there's more. And then there's going to be 2 phosphate groups. And then a ribose ring. And then an adenine, which I'm going to just abbreviate because we've already drawn it here. Okay? So why would nature put all of this on the other side of that thiol? And again, it has to do with the handle for the enzyme to bind to position the nucleophile in the right spot. This is called, this is involved in so many reactions in biology, coenzyme A, and almost nobody is going to draw it that way. They're going to call it thiol with a CoA on that side and assume that you can look up the structure if you're interested. So in terms of the reaction mechanism, we can abbreviate as follows. I'm going to just put OAMP here, and then the thiol I'm going to put here and just put CoA by it. Okay? So probably what has to happen is probably a base has to deprotonate the thiol, and it won't take a very strong base to do that because of course the thiol's pKa is around 8. Once that thiol is deprotonated, it should be sufficiently nucleophilic to attack the carbonyl carbon of the OAMP, and just keeping our general coloring scheme. There's the carbonyl carbon, there's the carbonyl oxygen, there's the leaving group. Get the tetrahedral intermediate, and then the best leaving group can leave. If you've been paying attention to the pKa's, the conjugate acid of the thiol has a pKa of around 8. The conjugate acid of the phosphate group that's going to leave has a pKa of around 7. So it's 10 times a better leaving group. And that's why when the electrons kick down, the AMP group leaves, and you're left with the coenzyme A thioester. You're going to see this or something like this again and again in our chapter on metabolism. And when you're thinking about how did we get the coenzyme A on there, first you had to start with the starting material, which was the acyl AMP. And we'll talk later about where that acyl AMP comes from. I alluded to it here. You end up using the carboxylate as the nucleophile, and ATP as the electrophile. And that mechanism isn't hard, it just doesn't necessarily fit very well with what we want to do today. Okay, questions about that? I mean, you should sort of be feeling two simultaneous feelings right now. Overwhelm at all of the structures, and then boredom that it's just the same reaction you've seen before a gazillion times, okay? So if you've got boredom and overwhelm coexisting in your mind, you're doing just about right. Okay? So okay, let's lean into the boredom part. Let me show you some nucleophilic acyl substitution reactions of thioesters in biology. Let's start with acetyl-CoA. This is a thioester in which you just have a methyl group on the carbonyl carbon. Now the thioester is going to be the leaving group, and we're going to be replacing it with some kind of nucleophile. So here is a 2-carbon amino alcohol in which the amino group is also fully methylated. This type of molecule is called choline. You've got a quaternary ammonium group on this carbon and then an OH group here. In this reaction, the alcohol is going to be the nucleophile. Why the alcohol instead of the amine? Well, because the amine doesn't have a lone pair on it anymore. And the product that you could predict is, and of course this is, again, an enzyme that catalyzes the reaction, the product is going to have the alcohol now involved in an ester, and we'll put these groups here. We'll use our coloring scheme to keep everything organized. The group that left is coenzyme A, first as the negatively charged thiolate, and then it probably picks up a proton from some source to become the coenzyme A thiol. What we've just made here is acetylcholine, which you've probably heard of as a neurotransmitter. And there are other enzymes that will come back in. They are called acetylcholine esterases, and their job is to hydrolyze the ester linkage between the carbonyl carbon of the acetyl group and the oxygen of choline. Lastly, I'll show you a reaction very similar using a thioester to make an ester. And notice the direction of these reactions. In general, nature is using a more reactive carboxylic acid derivative, a more reactive electrophile to make a less reactive carbonyl compound. We're going from the thioester to the ester. Nature will take advantage of this all the time. You invest the energy to make the thioester so that subsequent acylation reactions are downhill in energy. Another common reaction, this is how cholesterol is actually transported in blood, involves modification of cholesterol with a long chain fatty acid. So this is called fatty acyl-CoA. The R group could be 16 carbons long or longer. And then here we're going to draw cholesterol, which you can look up the structure, but for our purposes, it's an alcohol. Got a 6-membered ring here with an alcohol with that kind of stereochemistry. Another 6-membered ring there with a methyl group at one of the bridge carbons. Another 6-membered ring there with a down proton and an up proton. And go ahead and draw the chair conformation of that. You wanna? Actually, don't worry about that. We'll deal with that later. But as you can see, cholesterol is pretty nonpolar. And it's got a polar OH group here. And that is one of the reasons why cholesterol is good at embedding in lipid bilayers. The OH group can be exposed to the water and the rest of it can be inside the lipid bilayer. But for transport in these lipoprotein particles in blood. That's what your cholesterol test actually senses or measures, is the LDL and HDL particles. For transport, the OH group needs to get modified with something that's nonpolar. And so the strategy is to take a long chain fatty acid with the coenzyme A leaving group and then use the alcohol of cholesterol as the nucleophile. And what happens is exactly what you would predict. We don't need to draw the mechanism because you should be able to figure it out. Whoops. And because I don't want to draw cholesterol again, we'll just copy and paste, and I will show you the ester that's made. This is called a cholesterol ester. And this is what gets packaged in HDL and LDL particles and gets transported. Okay, so that was a whirlwind tour of acyl phosphates and thioesters in biochemistry. We also talked about bacterial cell wall synthesis. One thing we did not talk about is peptide or protein synthesis in the ribosome. And I think we probably won't do that because we don't have time and because that's a topic that I think is better covered in biochemistry anyway. So that sort of concludes chapter 16. Now we got a few minutes, and I think some of you probably have some questions that you want to ask about the exam. So let's take a few minutes and do that. I open myself up to cross-examination. Any questions you want?
Question number one.
Question number one on the exam. What do you think it is?
Oh, it's acetyl.
It's an acetal? The question number one on the exam is not an acetal, but acetals might be found somewhere in the exam. Other questions? Yes?
On the 13 problem set, there was an NMR thing. Is that going to be part of it?
On the chapter 13 problem set, there was a problem that required you to use some NMR. I do that to keep your skills current. Some of you that are taking 353 right now, that's probably not necessary. Others that aren't, it's good to stay in practice. I suppose if it's fair game to be on the exam, my guess is it wasn't super complicated. If you're asking, should you spend hours to go back and review the stuff in 351 on NMR instead of the current stuff, my guess is that's not the best use of your time. If you're asking, is there an NMR question on the exam, I respectfully decline to answer. How's that? Okay, yes?
Do organocuprates only react with acid chloride?
Do cuprates only react with acid chlorides for the things like acid chlorides, esters, amides, and so on? Those are the only examples that are given. I don't actually know what cuprates do to esters. That would be good to know, but I don't know. So for our purposes, the one reaction you have, aside from the alpha-beta unsaturated carbonyl compounds, is the acid chloride. Okay, others? Yes? 20 questions on the exam. Others? Yes? Can you write on the exam? Yes. Oh, this might be somewhat useful to you. You can write on the exam if you want to bring scratch paper. I recommend stapling your scratch paper to the exam. Some of you after the fact may want to come talk to me and say, hey, this is what I was thinking. Can you help me with my process? If you staple your scratch paper, we can go back and look at what you were thinking. If you don't, we have no way of doing that. So that being said, please do not count on this as an option. So what you shouldn't do, what you absolutely shouldn't do, is write down an answer on the bubble sheet and then hedge your bets by writing down another answer on your scratch paper on the off chance that you get it wrong, so you can come to me and tell me, well, I actually wrote the right answer here in the scratch paper. Don't do that. Your bubble sheet is what counts. But I am happy to look at your scratch paperwork. You can staple it to the exam if you want. Other questions? Yes? What is the average on the first exam? You haven't taken it yet, so what do I know? Historically, oh yes. So historically, the average tends to be around 80%. And we'll say more after the fact about that. Okay, get out of here. Have a good weekend.